Hello, my name is Richard Powell, and this is How to Argue Ment. This is one of these talks where I came up with the title a year before I came up with the talk. So I love the title so much, I felt I needed to do some slides about it. But really came from, actually, is more about thinking about functions, thinking about the lessons I've learned through doing code reviews and talking with people and doing my own learning about how to be a better programmer. And really, I think my main message I want you to take away for today is to think about the function signature. This is a small part of your code. Most of the time we concentrate on the larger body of the code, but think about your function statement, your function signature. And what I want you to think about is think about your function signature as being your thesis statement. It is your statement of what this code does. It should be very clear what the code's purpose is, both for the person who's going to call your function and for yourself when you're programming against it. I also think that you should understand that different types mean different things. And when we write our function signature, and being clear about your function signature does mean picking a good name for your function, but it also means making sure that the argument types that your function requires are harmonious with what the function needs to do. It means understanding what the different types mean, what their purposes are, and expressing both to the caller and to yourself when you're writing the code, what those arguments are there for. And I wanted you also to think about what your code means both to the caller, for the person who's looking at your code, and for the callee, for you who is writing the code. When you're looking at code, when I have to look at code, I end up having to look at a lot of code, and I want to be able to quickly look at a function signature and understand what that function's purpose is. I'm going to look at its name, I'm going to look at its return values, I'm also going to look at its argument types. And it should be able to tell me a lot about what that code's going to do. And when you're writing code, if you know what that function's supposed to do, your argument types can serve as an anchor. They can let you understand, okay, I want this function to do this, and now I've structured my thesis statement correctly. I'm going to now create code that's going to support my argument. Well, my thesis statement. So, here's some obligatory best practices. So I would want us to make sure that we're expressing an argument's purpose. We're trying to use the most generic or general type possible for an argument. And also, I would say a good guideline is don't surprise your callers. These are the guidelines which I'm going to use today when we talk about the argument types. And the way I'd like to talk about the argument types is by cataloging them, going through them, giving them each a purpose, deciding which argument types don't make sense, and then ending today's session with a list of argument types on which ones I would recommend that you favor. So let's get started. So given a function, f, badly named function f, what are all the ways to pass arguments? So what are all the ways that you can pass your argument types? Well, I'm going to put up a couple here, the obvious ones. So, and we have, you can pass by value. Pretty straightforward. Oh, and by the way, the T here doesn't mean template. The T here means any type. I wanted to have brevity on the slides. I'm not talking about templates or template deduction today. I'm just using this as a stand-in for any type. And that T type could be a primitive, like an integer, a double, or it could be a user-defined type, like a standard string or your own foo. It could be foo, or it could be even thread, or some sort of mutex. But T just stands for sort of any type that you would pass in. So given a function, you can pass by value. And if I push the forward button, you can pass by an L value ref. A way of, there was a little mnemonic that I learned years ago from another programmer, and I thought it was an interesting way to think of an L value ref whenever you see it. Whenever you see an L value ref, that is referring to some other variable somewhere in your code. So you should be able to look through your code and find it. It may be 3 levels up on the call stack or in some other translation unit, but when you see an R value ref, it is some named value in your program. You can also take by R value ref, and this is sort of the opposite of that. When you see an R value ref, in general that means a value that doesn't have a name, and these most often come up in the context of a return value. So when you see an R value ref being used, almost certainly it's meant to stand in for some temporary unnamed variable, value, object. And you can take by a pointer to an object. But this is only a little bit of the list. There's a whole lot more. We have our const versions of those, so you can take by const value, you could take by L value to const, or an R value to const, I guess you could. You could take by a const pointer. Pointer to const. No, it's a const pointer to an object. I'm missing const pointer. Well, let's fill those in now. So there we go. So you could, I'm just like, let's play on a theme. Let's give everything. Let's give the L value to a pointer, an L value pointer to a const, an R value pointer to a const, what else do I have on here? An R value, a const R value pointer to a const object. Well, we're not done yet. Why don't we should include all of the smart pointers in here. So these are all the possible ways you could pass in smart pointers. I'm going to talk about unique pointers and shared pointers. I think they're very important to have an understanding on because they express something unique. And I'm sure we could keep going and we could bring in expected and optional and all sorts of GSL versions of these, but we're going to tackle these today. So we have something like 42 different variants on a theme here. So let's go through and start giving these specific names and talk about them in detail to determine which ones conform to our guidelines of that we should use and which ones don't make sense. And the way we're going to do it is I'd like to sort of give each of these types a sort of a nickname or some sort of way of thinking about it. When you see pass by value, what do you think that this means? Copy. What other way would you express that? Like sort of, yeah, it's making a copy, but is there another way to talk about it that way? I mean, you got a copy. There's some other. Sorry? Input parameter. Sync. You got to speak up. It's very hard to hear in this room. T is not changing. T is not changing. T is not changing to who? To the caller. I actually call this a snapshot. Maybe it's not the best name, but it's a name to think about it. We're taking a copy of the value. We're taking essentially a little bit of a snapshot of the state of the program, and then this function is now going to operate on it. And so one of the very nice thing about this function is that we have a high degree of confidence that the caller, or the callee, is not going to interfere with the state of the caller. In fact, actually, when I look at this code and I'm scanning for bugs, I know that I'm like, oh, that's a T, great. I don't have to worry about the calling function modifying anything else outside the program. It's been given a little piece of the world that it can play with. What about these two? Is there any difference? Do we like one versus the other? What do they mean? What does the const mean here? You just yell it out. It's information to the callee. No, it's not.
No, these are both declarations of a function, and those are the same type thing.
Yes.
The callee, not caller.
Yes, the callee, not the caller. So the comment was that these are both the same type signatures. In fact, actually, they are in fact the same as far as the compiler is concerned. So from the caller point of view, they're not different. But there was an interesting comment about from the callee point of view. Within the body of your function, they are different. And maybe this could be your company's best practice that whenever we have our functions that are taken by value, we declare them as const. I don't know if we need to go that far. I don't really know if, I think that the one on the left is sufficient for describing what the function does. It's given a snapshot. If your coding styles say, yes, every time we have a variable, we always name it const, that might be a good best practice. But in general, when I'm looking at code, I usually see the one on the left meaning it's taking a snapshot, and the one on the left actually gives me a little bit of a pause. So I favor the one on the left, and I think that's the one that is going to be satisfactory for most of our declaration needs. What about this? This is our favorite. Anyone want to give it a name? View. View. I like that. I called it observe. I also put a little asterisk in between here about how it's observing it during the call. We're going to come back to that. So what this is this is a reference to a variable. It is from when I see this, I see that the caller, I'm granting the callee a little view into my object on the program, and it's promising that it won't modify it. So it's going to observe it. Which of these should I use? Depends. Size. Anyone want to take any? It depends on how expensive the copy is. It depends on the size of T. What if it was tiny? Like, what if it was an int? Pass by value. What if it was an extremely large function, but I don't know what the function, or object, but I don't know what the function does? let me illustrate that sort of with some points, and to say that this is not an easy question. So looking at Compiler Explorer, so I have a function do work, which doesn't really do any work. It does a comparison and then returns a value. And it returns the same input value in both cases. And so we hear the compiler is much smarter than I am and is able to determine that there's nothing to do. So it simply copies the input argument from a register into the return value and returns. Wonderful. And let's say I pass this by const ref. So what we see here is that there's a dereference that occurs because the reference is essentially a pointer as far as the machine is concerned. So not a real big surprise here. But what if I introduce a function call in the middle of this? Now, so what we see here on the code that's generated is we see the test, so it's going to check to make the comparison. And there's a little bit of stack manipulation that occurs. That input argument is put off to the side so that it can do the branch. It returns, or if it fails the branch, it will do the call. And in both cases, it rearranges the stack restore, and calls. And this is maybe a little bit of an optimization the compiler did for these size objects. It could have maybe done the comparison and returned early, but in terms of pipeline, it may be more efficient for this machine to do some register moves which are excessively cheap, and then just return. So we see something different when I pass by const ref. In this case, what happens is I see that it does a dereference, reads out the value from the pointer, or the reference. It does its test, branches. In the case where it is greater than 0, it does the call, and then it does another dereference. Why did it have to dereference again? I mean, I never changed. It was declared const. Input might be global. We don't know what is happening. We made a function call, and we don't know what the state of the program is after that call. For all we know, that the value of input could have changed. To illustrate that point, imagine here's my function in isolation. And I have some function foo, which increments a global variable. And then I call my function, I call do work in this way. So at this point, the program has actually manipulated the global state, and the compiler would be wrong not to reread that value. So when you pass an object by reference, you are forcing the compiler not to be able to take all of the optimizations it could. When you pass something by value, it can make a lot more assumptions about the state of the program and actually really crank up the optimization level. So in some situations, when you have a large object, it may be better to make a copy to work on. But the real test is always going to be profiling. There's no good guideline here that's really going to work. I mean, for primitives, I think we can understand that, yes, it's probably going to make sense there. But for medium-sized objects or even starting to get on the large objects, it may actually be better to make a copy. So my advice on this is to pass by value when you can and pass by const ref when you must. And I do understand that's rather unsatisfactory, but it all comes with experience, profiling, and looking at what your code's doing. Do I have a benchmark to test this? I don't have a benchmark to test that particular thing. But I would strongly encourage you to benchmark your code on your particular cases. Pass by reference. What would we call this? What? Output parameter. Ooh. In-out parameter? Ooh. Maybe could it be used in other? Is it always an output parameter? Is it always an in-out parameter? What do we know it's doing? It might modify. Yeah, I call this modify during the call, or I didn't even, yes, it could even be, it may not modify. And this is one of these things that, like, I put this slide up before and people say, oh, I would never do this. I never write code that takes a parameter by reference. But I think we all do. We may not know it or not. But we all write something that looks like this. And once the compiler's done name mangling, it sort of looks like this. And that effectively, even though it's called a this pointer, it can never be null. It's effectively a reference. So anytime you're calling a member function that's not const, you're effectively potentially modifying that value. So I bring this up just to point out that we may not be doing, you may be doing this inadvertently, and it's when you're writing a member function, effectively you're saying that this function is going to modify the state of this object. So, pass by our value. What would you call it? Maybe move. Maybe move. Ooh. Technically, yes, it's a maybe move. I was thinking of something simpler, but that is pedantically correct. I don't want it anymore. I don't want it anymore. It's yours. Take it. I call it a sink. And Titus is shaking his head saying, it's not a sink.
Only if it's in an overload set.
Only if it's in an overload set.
A const ref plus ref overload set is a sink. A T is a sink. A T-ref by itself is a maybe move.
A T-ref by itself is a maybe move.
There is only one example of that in the standard library, and that is for functions that are specifically called try, because they are maybe moving their thing.
So the comment is that...
Replace or try update.
So it's a maybe move. I've usually seen, when I see now a value, when you're taking a object by ref, our value ref, I usually have seen it in the context of a move, it's you're moving, but there is the chance that it might not be actually moved, to Titus's point, which is, yes, in general, there's always the chance that the callee function may not do anything with it. But in general, when I see this code as I'm scanning through, I see that and I think that's probably passing the ownership of this object to this thing. It's implied that I'm giving it over to this thing. Or more correctly, if I see a function that has the signature and it's being given an object, I know that I shouldn't be using the object after that point. Or I very likely shouldn't be using the object after that point, except for some extreme cases. So what does this mean? My generics have gotten out of hand is the comment. Something like that, yeah. Actually, I think if this is causing you to feel a little queasy and you're like, this doesn't, like, I don't understand this, it's because this is sort of nonsensical. This doesn't really make a whole lot of sense. So when you want to move from something, or maybe move from something, what you're going to probably do is you want to move from that object. And when you're moving from an object, you're effectively stealing the guts of an object. And a const R-value ref doesn't allow you to modify that object. And so this is nonsensical. It does make sense in very few contexts. If you know what this means and you're using it, then you probably have a very good reason for doing it. But in general, this is not something that you should normally see or know or use. See or use. So I don't think that this is an argument type that you should be using unless you have a very specific reason for doing it to avoid some operator overloads. Passing by pointer or const pointer? You want to take a guess at what you would use this for? Might be null. Optional. I call it optional. Well, during the call. So then you get to the really good question of, sorry. Should be looking at my builds. Yes, so this is an optional. This could be an argument that it's either the value is there or it could be null. So what it's saying from a caller point of view, when I see this as a caller, I say, oh, I have the option of passing it null for it, and it should handle it. And from the caller point of view, what you're saying, or callee point of view, what you're saying is, you can give me a thing, or you can not give me a thing, and I will be okay. But you should not use this as an output parameter. You shouldn't be saying, oh, here's a place where you can put a result. There's a perfectly great place for putting results, and that's on the left-hand side of the function. You can put there, if you want to give a result, that's the place you should put it. You shouldn't put your results on the, as an argument, you should put them as the results. They're called results. And you shouldn't be doing any lifetime management with raw pointers. We have a whole bunch of great smart pointers for doing lifetime management, and we'll get to those. So, let's talk about optional. Which of these should you use? They weren't, I didn't include optional in my original list, but let's pretend. Should you take by optional? And I'm actually genuinely asking that too, because I'm not quite sure about this. I haven't had a chance to fully digest this, but what do we think?
The one on the right requires a copy.
The one on the right requires a copy. Yeah. So I think of it as, going back to our principles, which of these is more general? Which of these can be used by more callers? So with optional, I can pass a thing that is copyable. So it can be used like this. So sort of seems like it's okay. It could be used in those contexts when I want to pass a thing. It doesn't do so good if I want to pass not a thing. Well, I can fix this. I could write it like this and to indicate this is the not a thing. So if I have a function that takes by optional and I want to express that I'm not giving you something, I could give it the default. But one of the things is optional doesn't do what the pointer does, which it doesn't allow any modification of the original object. It's taking a copy. It's not actually taking that thing. So if I did actually want to use it for, I'm manipulating that object, if I am modifying that object, I can't with optional. I mean, I could take by optional ref, or I could take an by the tref optional, but in both those cases, I can't get the implicit conversions that would occur if I passed it a normal object. And if it's an object that can't be copied, I can't pass it implicitly. I would have to wrap it in some way. Now, these are, now I'm trying to figure out why I'm passing a mutex by const, which actually I don't think makes a whole lot of sense. So maybe that's the problem you get with adding slides the day of. So there should not be a const in this case. But my point on this is, I think if you want to express that an argument could be optional, favor the one on the left. The one on the right, the optional one, has a little, it's not as expressive, it's not as general. Yes?
Would you get into the same optimizer problem you mentioned earlier, where if T is an int, right, and you pass in an optional int, then by value, then the compiler is going to be able to not have to reload that argument as compared to the address.
So the question is do you get into the same sort of problems of potential aliasing and the global state if you passed in a pointer versus an optional? Well, so if you were to pass in a optional, that, like this is actually a value. So it is a it is a copy of a value. So it's either that value that I've made a copy of or nothing. So the compiler this is technically more like passing by value. Here I'm actually passing in some object that's outside of the scope, and the compiler can't make the same assumptions. But that's not sort of the same thing. This is so that does actually have a point, which is this way I can express both a passing by value and making something optional. So yes, it is true that if, so the comment was that the earlier example where I passed by value, or I passed by a reference, and there was a function call that occurred between the reads of the reference, the compiler was forced to reload, and the same thing would happen if I passed by a pointer. Yes, the same thing occurs in both those cases. So then the question is, well, wouldn't this be better then? The one on the right be better in that case because I'm getting that level of optimization, but what I'm saying is, this is more like passing by value. The one on the right is more like passing by value, but it's able to express that it may not be, it's sort of like a different sort of semantics, like saying, I am giving you a copy of the thing, or I'm not giving you something.
So it's an optional snapshot.
It's an optional snapshot. I like that. So it might have a place, although that seems rather very specific. But if you did need to express that this function is optionally snapshotted, that could be a way to do it. There may be others. So. Passing by const ref to a pointer. So we're going through our list. We made an exhaustive catalog, and we're going through each of them and looking at them. This seems odd. This makes me feel like it doesn't really make sense. And what it is here is a reference to a pointer is a pointer to a pointer, which isn't, it's just a pointer. So think about it, it doesn't really make sense, and it's not something you would normally see, and it's not something you should use. It doesn't express anything different than just passing by pointer. So I think we should remove it from our list, and passing by an R value ref to a pointer.
Okay, I agree. Go back one. So that is a pointer to a const, a reference to a pointer to a const.
A reference to a pointer to a const.
So if you wanted to modify where the pointer pointed, use case.
Hold on.
Okay.
Hold your. We're getting to it. If I don't get it by the time I get 4 slides in, then you can stop me again. So passing by R value ref to a const pointer. So a pointer is a primitive. It's like an int. Well, different than an int, but it is something that is copied when you try to move. Instead of getting a move, you actually get a copy of that. So it's just a primitive value. An R value of a primitive is, there is no move that occurs. You effectively get a copy. So this syntax isn't really saying anything different than if you had taken it by pointer. passing by L value ref to a const pointer or a pointer. So this is odd. This is really, so what we're doing here is we're saying is, what I'm going to do is I'm going to give the caller, or the callee, a pointer that it can modify where the pointer points. Never do this. Well, I should say you should really not do this unless you really know what you're looking at. This effectively is reseeding a pointer to point somewhere else. This really interferes with the lifetime semantics. You may see this occur in the bowels of an allocator, where what you need to do is, if you're reallocating, you're saying, I'm going to take the memory that, this pointer was pointing over there, but I'm now going to make it point over here. This can be very hard to trace lifetime problems. If you're taking values and manipulating them this way, you should really know what you're doing, and I would say that this isn't something that we would normally express. There's a better way to express this. So, we had our gigantic list, and we eliminated some of them, so let's cross them off the list. Don't need by const value, we can get rid of that guy. How about these ones where I was taking, these are all const values. As we had said, the signature for these is always going to generate the same, so we can get rid of all of these. And what about these ones? These were R values that were const R values. These don't really make sense, so we can get rid of those. They have a place for template programming, but they don't really have a place in normal programming. And what about, what else was on the list? Right, the const, the reference to const to pointer. Those don't make sense, we'll get rid of those. And finally, yes, the R value refs. Those don't make sense. And is there anything else that didn't make sense? Right, these. The reseeding a pointer. These are ones that we shouldn't be using, so we'll get rid of those. All right. Well, I think we've cleaned up the table on the left pretty well. Let's start tackling the table on the right. Lifetime pointers, smart pointers. These are the pointers that we can use for expressing lifetime. We're talking about when we use these pointers, or when you use these pointers as arguments, what you're usually talking about is something about the ownership of that object. You're expressing either, I'm transferring the ownership, I'm going to participate in the ownership's life cycle, or I might be participating in the shared ownership of that object. So, when we pass by unique pointer, what do we mean? And a hint, I just gave you the answers. So it's one of those three. Transfer ownership. So when you're passing something by a unique pointer, what you're saying is, I have this thing, I used to own it, but now you should own it. And what about this? If I'm passing by a const ref to a unique pointer. Meaningless. Very close to meaningless.
It's very close. Like, it's meaningless. You shouldn't do it.
You shouldn't do it.
Unless, for some insane reason, you need a function that needs you to prove that you own it, but isn't going to take ownership.
I'm going to say it's meaningless. I didn't hear the rest. Talk to Titus later if you want to hear the full story. No, but actually this, I will say this, when C++ 11 first started coming out, I ran into something similar to this, and I found myself a little confused about what I was supposed to do. So I have here's my good old C++ 98 code where I had a factory function that would make bars. And what I was doing was I was logging some stats on that bar. So, and I had to manage my memory. I could have used auto pointer and all these potentially difficult things, but bar in this case is some polymorphic object that needed to be created at runtime. And it is, it uses some parsing algorithm underneath the hood to determine what bar it should use. So C++ 11 comes out, and I'm super excited, so I read something about how I should make return my factory function objects by unique pointer, so I do so. And then I find, oh, I should also now start using auto, and I've changed my return type for my make bar to an auto. Everything's great, except my code still doesn't compile. My logstats function doesn't work. And I was reading, it's like, we have a unique pointer now, I shouldn't be using any more raw pointers. So, but then this function takes a raw pointer. Okay, well, I guess I'll have to change it to this. And that just didn't feel right. So you shouldn't change your function signature to take by a ref to unique pointer, or a constant ref to unique pointer. Instead, you should take by a raw pointer. But aren't raw pointers bad? Didn't we got unique pointers so we didn't have to use raw pointers, right? Well, you shouldn't use raw pointers for to express lifetime and ownership, but a raw pointer for expressing observability, or in this case, optional observability, is perfectly fine. It's completely appropriate. And to use it, what you would do is you get the raw pointer out of the unique pointer to pass it along to your code. This actually makes, so in general, you should not use these, but instead you should just use pointers.
You're saying observability, that includes mutability too.
It can include mutability. But according to our previous guidelines, if you wanted to modify those objects, you can take it by pointer, but don't modify its lifetime by calling delete on it.
Right, no, yeah, I meant call.
Yeah, I have an object, I would like to modify it, or I should say, my function can handle being given an object or not given an object, but I'm going to modify that object. Pointer is the right type to use there. So then, what about this? Going through our entire list of our taxonomy, does this have a place? Where I'm taking by R value ref to a unique pointer. And I don't think it does. Wrong. So a unique pointer has to be passed by R value. Anyways, you effectively are going to be passing it by R value, and passing it by value, passing it by a unique pointer itself is more clear about what you're doing. You're passing this to that function, and by taking it by R value, it doesn't make as much sense as by taking it by unique value itself, unique pointer by itself. So my claim here is, so there are I should say, when discussing it, there are probably some cases where this could make sense, where you're forwarding it along to something else who might be forwarding it along to something else. But in general, when you're looking at code, you probably wouldn't use this form of the argument.
I think the core guideline refers to this as may take ownership.
So the core Jason Turner's comment is the core guidelines may refer to this as may take ownership. May take ownership. Maybe orphaned. Well, then it'll be destroyed. It won't get orphaned. Eventually, it'll be destroyed. Yeah, it gets moved into this object, and eventually will get cleaned up. Somebody can either own it or not. Potentially, yes. This could be may take ownership, but for the purpose of reducing our common argument types, I'm going to say this doesn't really fit in our common lexicon. Although, maybe if there's a version 1.5 of these slides, this should be added. Taken by share pointer. Shared ownership. What do we think of this code? Yes? So the comment is, I don't like this. It forces the ref count up. It unnecessarily forces the ref count up. And that can be a performance problem. This is, if you aren't going to participate in the shared ownership of this object, don't take by shared pointer. But sometimes you don't know. The callee should know, but sometimes the callee doesn't know if it's going to take by ownership or not. It may, depending on the state of the program. In this case, it's very clear. The callee at this point knows that it's not going to, so it shouldn't be taken by shared pointer. Almost certainly here, you would take it by just pointer. But what if there is a case that I don't know if I'm going to need to own this thing? Or I don't know if I'm going to need to maybe own this thing. Sorry. Where the callee doesn't know if it's going to participate in shared ownership of that thing. That's this case. This is the optionally sharing the ownership. So when you take a shared pointer by const ref, you're saying is, I might be taking ownership of this thing. For example, so imagine I have some do work function, and I'm going to take a shared pointer by const ref. So it might be the case that I'm going to run some background task, and I'm going to need to keep that object alive, or it might be I'm going to process in place here. So this is the type of, when you don't know if I need to increment the ref count or not, take it by const ref. And then when you've determined that you do, start background calc here probably takes by shared pointer itself, incrementing the ref count and keeping that object alive. So passing by R value to shared pointer. So again, this is similar to the, am I forwarding something along? I might be taking ownership of it. But I was like, is this a sync? I'm not sure exactly the way to express it. If you wanted to do this, you would probably either, as a caller, you would either say, I'm taking it by shared pointer, or I'm taking it by const ref. Probably likely you would say taking it by shared pointer itself. And finally, the big old taking by L value ref to a smart pointer. So what would these express? Reseat. So it goes back to our sort of, when I were taking a pointer by ref, we said, oh, don't do that because it interferes with the lifetime semantics. But here, we have the lifetime semantics expressed, so what these could be used for is saying, okay, you've given me a unique pointer, I am going to change where that object is. So this could be like if you have some polymorphic object that's been allocated at runtime, and your function here is like, I'm going to figure out a better object for you to use, it would give this back. Although, I guess you could argue is maybe it would return it as a result. But, or this could be for reseeding where an object lives. I would also add this is probably exceedingly rare to see in real code. I've never seen code that does this. So, let's go back to our table. And what can we remove? Well, we said we could remove the const ref unique pointers. So let's get rid of those. And let me go check my build before I click the next button. Yes, good. I have a really great animation. I just want to make sure we all see it. We're going to remove the R value for unique pointers. And we're going to remove the R value for shared pointers. Okay. So now, I think we have reduced our table. We started with, I think, 42 items, and we're down to 16. A lot of holes in here. Let me arrange things into a more appropriate order. There we go. Thank you. So we have our, and I've actually gone through and labeled them in a way that I think, from what we talked about. So we've got our pass by value, which snapshot or copy. You have your observer types. You have your modified types, both the optional version and non-optional. You have your values where you're syncing or transferring the ownership. You have the argument types where you're sharing in the ownership, the argument types where I might be sharing the ownership, and the types that where you're saying I'm going to reseat where this object lives. And also I think that, I also put it in this order because I think when you see normal code, this is probably the distribution of where you would see. Almost certainly, you should be living day to day when you're developing your argument types in the upper left-hand corner. If you're living in the lower right-hand corner, I feel very sorry for you, or your job must be incredibly fascinating. Avoid surprising your users. So I wanted to actually take a moment to talk about this because I think it's we sort of glossed over taking by ref or by pointer and saying it is an observer during the call. But we didn't really go into deep details on that, and I want to just spend a moment talking about that. So let's say I've got some function here that do some work, and it's taking it by ref. And when I see that, I get really suspicious unless I know the programmer, because that looks odd to me. I don't know what's going to happen outside of that call, because it could end up looking something like this, where what happens is the person who wrote foo is actually taking that input and putting it into some global variable and keeping that reference, that object alive, or makes the assumption that that object is being kept alive outside of its call. Okay. So this, for me, is surprising. And what this means, why I want to dwell on this for a moment is, if you're taking something by const reference, or if you're taking something by reference, or taking something by pointer, as a caller, you should only use it in the context of that call. After that call is ended, you shouldn't refer to that value anymore. You shouldn't be using that object outside of the call. But I do actually have, and I've been guilty of this, wanted to have some sort of class object hierarchy where I have a parent-child relationship. And you can express the same sort of thing with smart pointers, with shared pointers. So this could have been written this way, and with shared pointers and weak pointers, to indicate I want to participate in the lifetime of this. I'm going to keep a weak reference to the original object, and when I need to use it, I will make a strong reference to it. So if you find yourself needing to keep an object alive outside of a function call, use smart pointers as your argument types. Don't use pointers or references. Instead, reach for lifetime pointers to express what you're trying to do. And same slides to express that. So here are my guidelines from the talk. I think it's really important to emphasize what I'm talking about today is just make sure you know what your types mean and give your arguments type. They're trying to express something so that when someone's looking at your code quickly, they understand what you're trying to say. And also, you should understand your type so you can say the correct thing. I would say pass by value when you can, pass by ref when you must. When must you? There's no easy way to explain it. You're going to have to do it when it's a polymorphic object. You don't, all the rules of C++ 98 still apply. You don't want to be slicing if you're taking by value of a polymorphic object. But profiling and benchmarking is really going to be the key to determine if you should use by value or if you should use by reference. Using raw pointers for optional, but don't use them for expressing any sort of ownership. Use smart pointers for expressing ownership. Oh, and return your results. I don't recommend having an input or an in-out argument or an output argument as a pointer. If you need to return something, there's the entire left-hand side of the function signature for you to use. And don't use a pointer or a reference outside of the call context. If you need to do something like that, shared pointer and weak pointer are what you should reach for. And this is the table of types for arguments, and I'm going to leave that slide up and answer questions. So thank you. And there's a microphone at the front for questions. Destroy me.
No.
So Titus mentioned that in some cases of complex overload sets that some of these signatures might have other meanings. I was wondering if in any case if you're trying to make your API particularly robust, you might explicitly delete some of these so that they can't be used, like const R value reference.
Yeah, that is, so should you delete const R value ref in general, or should you do it in only specific context?
In a specific context, if you want to say like, no, if you're passing me a const R value reference, you've done something terribly wrong here, I'm going to just delete that so it doesn't pick the const L value reference.
Right, and I think that can come up in the context of where your, well, R value forwarding references are notorious for swallowing everything. Right. And so when you're doing if you're writing a forwarding reference and you want to explicitly say something is deleted so that you can catch any sort of compile time warnings, that's a context when you would use it. So if you were to, you may see in meta template or template metaprogramming code or some larger types that where the taking it by const R value ref actually has a significant meaning. And I've usually only seen it in the context of where saying don't do this, where it won't accept it. It's usually been deleted. And actually, I'm not familiar with in a context where it has a meaning for when you wouldn't delete it, though.
Yeah, that's what I'm saying. Just how often
Yeah.
do you recommend using delete to remove things from overloads in these APIs, or would you?
Actually, I don't know how often you would do it if you were doing your regular sort of object. Is not like a general guideline of, I've written a new value type, I should now delete this overload. I don't think it fits in the general usage pattern. I think it fits in some very specific patterns when, well, Titus might be able to mention a couple where it actually makes sense. When would you delete it, Titus?
Very rarely.
Very rarely.
This is something I thought about recently, so I thought it made sense.
It might make a great,
There's a chunk in my Monday talk about it.
yeah, there might be a great lightning talk. That sounds like a great lightning talk. And go see Titus's talk to get more information. Are there any other questions? Yes? Oh, microphone's great if you could use it.
What you mentioned, it's beneficial to return by return value, right? So don't return by reference. But I have a quite practical struggle. For example, I want to read from database, and I want to return data, and I want to like reuse the same buffer. So technically, I can return this by value and create every time I create a new buffer. Yep. Or I can reuse the same buffer again and again. So what's the recommendation?
Yeah, so there is the don't reuse the, don't give a pointer when you need a return value. However, the classic example like getLine is like so much more efficient if you do so. And that's definitely a challenge where you do have this, I have this place in memory that I want to put my result when I'm reading as opposed to constructing a new object every time. And yeah, that is I think that Eric Niebler had a very interesting talk on that about creating an object that manages that data for you. So it's changing the sort of, I'm not taking it by return value, I'm having a stateful object that maintains that result. So I can call it continuously. And so you sort of hide that detail from your caller, but what you're doing is saying, I have an object, but what you're effectively doing is reusing the object's memory. So I think that was the CppCon talk 2 years ago. Or maybe it was a blog post. I should probably know. Any other questions? All right, thank you.